All right, it is 9:30 on Thursday. Our exam is a week from today. First exam, chapter 6 and one section of chapter 7. So we'll finish up chapter 6 today and we'll see how far we get into 7.3. We should be able to do most of it. The 7.3 is the hyperbolic functions, and the hyperbolic functions parallel the circular functions. So the 6 trigonometric functions are called circular functions because they're based on a circle. And then there are 6 parallel hyperbolic functions. The formulas look very similar to the circular functions, but they're called hyperbolic functions because they are based on a hyperbola instead of a circle. But there's a lot of parallel things going on with them. So that section is not too hard. It's mostly just the derivatives and the integrals that we're going to look at and look at how they compare to the trigonometric derivatives and integrals and just sort of get comfortable with it. There's really one hyperbolic function that you all have used and seen that we'll focus on more than the others. But we're not going to do a ton of hyperbolics. It's kind of a one-off topic. The one function, the hyperbolic cosine, is the one that you've heard of, perhaps. Okay, let's finish up with our other section, 6.7. So we went about halfway through. We talked a lot about the work for. Let's look at the main examples again, just for a moment, just to remind you. So let's look at the example right here of a cone. That's a pretty nice one. So let's just remember where we are and how this formula worked for the work in pumping the water out of a cone. The acronym that we are going to use is ADD volume. So anytime we've got a three-dimensional vessel, a cone or a trough, and we want to pump the water out or drain it out the bottom, both of those would be done with this formula. And remember that it's acceleration, density, distance. And when we say volume, we mean the volume of a cross-sectional slice. So the cross-section's two-dimensional, and then we add thickness by putting the differential on it, and that takes our cross-section right here and turns it into a slice, turns it into a mini volume. So that was our procedure, and the basic thing you have to remember, which is also going to translate to the applications we do today, is that our elements are always horizontal with these applications. Because we're looking at a cross-section where the particles of water all travel the same distance if we're pumping out the top. So that's kind of the idea. We want to take this cross-section where distance traveled for each point in that cross-section is uniform. So that's why everything's going to be horizontal for these applications. And we know, based on what we've done prior, that if things are horizontal, we need to solve for x for any of the bounding functions, any of the functions that are bounding our horizontal cross-section or horizontal slice, whatever way you want to think about it. So that's why we're solving for x here. So in this case, we had to find the area, the cross-sectional area of a disk, and the distance over to this diagonal line, that's going to be the radius of the disk. So we solved the edge equation for x, and that was then the radius of the disk. So that was one vessel. And then let me remind you that with this vessel, things were a little bit different for our cross-section. So the cross-section of that cone, we needed half the distance across the whole thing, right? We needed half the distance here because that's how you find the area of a circle. You only need half the diameter. You need the radius. So we only cared about getting from the edge of our vessel over to the center line. Whereas with the trough, it's a little different, right? With the trough, when we take our cross-section, the cross-section was a rectangle. And the area of a rectangle is width times length. So we needed this whole distance across the face here, the whole distance across this vessel. Not just to the middle. Not just to the middle here. We needed the whole distance across. Again, it's a horizontal element. And anytime we have a horizontal element, we're going to do right minus left. And we're talking about x values. So the right x minus the left x. So we write each of these bounding curves. These curves are bounding this element. So we have to write that curve as an x value. We write that curve as an x value. And then to find the entire width across that chord, we do the right x minus the left x. Positive square root minus square root gives us 2 square roots. And that's how we got the distance all the way across. And then the cross-sectional area, again, it's a rectangle. So the area is everything in here except the dy. It's the width of our rectangle, which is that thing up there. And then the length is 3, so that gives us our cross-sectional area. And then to turn that cross-section into a slice, we multiply by dy to give it a little bit of thickness. And so then that gives us the volume of our slice. And then again, it's ADD, acceleration, density. These are both given, metric system. 1,000 for density of water, 9.8 for magnitude of acceleration. And then that is the distance your cross-section has to travel. So if this vessel was 1/4 of a unit deep, if we draw a representative cross-section at y, for the water to get out of the top from that cross-section, it travels 1/4 minus y. That's the distance traveled. And then the integration is what it is. We had to use substitution. So those were that's the main idea with these problems. Let's just review the rope for a minute. Let's look at a chain. And let me just remind you, as you've hopefully started looking at some of the homework, we have 3 different types of density problems. We have 1-dimensional density, 2-dimensional density, and 3-dimensional. And all those water problems where we're pumping water or draining water, that's 3-dimensional. So we're using that 1,000 kilograms per cubic meter. So that's a 3-dimensional density problem. With these chains and ropes, these are all 1-dimensional density problems. We don't do any 2-dimensional ones in here. You'll do those in Calc 3. The 1-dimensional ones, the clue is that the density, so if it's a rope or a chain, they're giving us the density in terms of kg per meter, not meters cubed. Right? When we think about the density of water, it's kg per meter cubed. It's a 3-dimensional density. Whereas with the cable or the rope, 1-dimensional. So that is our clue right there. And if they happen to throw in the diameter of the rope or the cable, we know that that's extraneous, because right here they're telling us it's 1-dimensional. So an element of rope or chain is just a dot. It's a single point. And then if we add the thickness to it, the dy, that's what's going to give us length. So instead of ADD volume, we're taking away 2 dimensions, right? Instead of a meter cubed, it's a meter, so we're taking away 2 dimensions. So instead of volume in the parentheses here, this is the length, which is always just dy when it's length. So that's how that rolled out. Now, somebody asked there's a couple of questions that come up with this kind of thing that let me just address. So if we have our rope hanging, and we calculate the work done in pulling it to the top of the cliff, or winding it up on a winch or whatever, so it's dangling, it's not plopped on the floor, it's dangling like that, and we pull the whole thing up, we get the work that we got right here. So here was the question. Somebody asked me, well, what if we just drop the rope or the chain? So we're not going to coil it up, we're just going to drop it. How much work is done in that case? Same work. Same work if we pull the cable up or drop the cable. It's just that gravity will be doing the work instead of the winch or the person pulling it up. But it will be the same. The only difference in here, let's visualize, okay, there's an element of rope right there. If it's going up to the winch, the distance it traveled was 30 minus y. How far, if we just drop it, an element at height y, how far does it travel? Y. It just travels y. If you've got your element of rope at height y and you just drop it, it goes y down. So if you did this integral and you replace the 30 minus y with y, you will get the same exact answer. Okay? Because the work done is going to be the same. That will be the same. Now, the other piece of this that I want to mention is that Same is true for this shape. If we are dealing with a shape that's symmetric in this, if the cross sections are the same all the way up and down, so it's symmetric in that sense, like every cross section is the same in area. Same thing here. If you pump the water out the top or drain it out the bottom, the work will be the same. So in this integral, if you replace the 8 minus y with y, you will get the same answer. So the 8 minus y is the distance that the water would travel to get right out the top edge. And this slice is at a height of y. If you drain it out the bottom, that slice has to travel y. So if you replace the 8 minus y with a y, you'll get the same answer because of the symmetry of the tank there. Now, if we look at the trough or the cone, let's look at the cone. It's a little easier to visualize. This is different. This has cross sections that are different in size. This one, do you think more work will be done pumping it out the top or more work pumping it out the bottom? There will be more work draining it out the bottom. Why? Well, if we think about the biggest cross sections are at the top. The main variable here is the main thing that's variable is the distance traveled by each slice. Right? That's so the distance traveled by this slice. Here are the big slices up here, and they would have to travel further to get out the bottom than to get them out the top. So that distance function is going to be bigger, and these slices are also bigger, so that's going to contribute to it being more work to pump it out or to drain it out the bottom. Now, the work would be done by gravity, so that's easier, I guess, in that sense. Mechanically, it's easier. But the work done pumping out the top versus draining, the work done by the pump is going to actually be less because the bigger slices are at the top and they travel less distance. So you can think about those two symmetry things, though. With the cylindrical tank or with the rope or the chain, you have this weird thing that you could do with the, you could think of dropping or draining instead of, coming out the top. Okay, so let's go to our trapezoid force problems, because these are super similar, but those ideas are important. So on Tuesday, we talked a little bit about hydrostatic pressure. I definitely recommend watching those two videos in the discussion area. Those are very good. And we talked about how hydrostatic pressure pushes with the same amount of force in all directions simultaneously. So if you imagine adjacent molecules of water, they're sort of canceling each other out. This one's pushing this way and this one's pushing that way. They sort of cancel. And so that's why it doesn't matter how much water is behind the dam. You can have 1 foot or 1,000 feet, and the force on the dam is the same. So we only care about that face of the dam. It doesn't matter how much water is behind it. We're only interested in what's happening right at the face. So we're going to use the same trick, the same acronym that we used when we were doing the pumping problems. Or similar. It's ADD area instead of ADD volume. It's going to be very similar. So the idea, again, we're going to use horizontal strips because at a horizontal depth, same pressure, right? Same pressure across there. So that's why we focus on a strip. The pressure along this strip is the same wherever you are. And then we imagine the strips getting thinner and thinner. And so then we have constant pressure. And we figure out the force at each cross-sectional strip. And then add all the forces up to get the total force on the wall. So we imagine the force along each of these elemental strips. And then we're going to add them all up right there. And that's going to turn into a Riemann sum, which then turns into this integral. And just like the pumping problems, this integral feels really gnarly looking. So we're going to come up with the acronym that's going to make it much easier. The basic idea, though, is that if we are looking for force, all the units inside the integral, including the differential, better give us units of force. And they will. So pressure times area will be force, because when we think about pressure, pressure is force per unit area. If you're submerged in a pool, what you feel is a force per unit area. That's what pressure is, force per unit area. So in the context here, we're going to think about force. Instead of mass times acceleration, our force is going to be pressure times area. That will give us force, pressure times area. And the units are all, I've got a couple explanations on the units, and you can look at the units here. You can also look back at this slide right here where it says rope. This has the units broken down also. So when we're finding work, we have ADD volume. When we're finding force, we have ADD area. That should make perfect sense because if we multiply by one more dimension of length, area will become volume, and we know force times distance is work. So if we added one more distance in here, then the area becomes a volume, and we've gone from force to work. So that's our focus. And if you look at the units inside the ADD area, the ADD limit, ADD units will give us units of pressure. They call units of pressure pascals, but we won't use the word pascals in here. You'll see that in physics. But the bottom line is ADD will be units of pressure, and then we have area, and pressure times area is force, because pressure is force per unit area. So thinking of the inside as pressure times area, that's our check. Okay, pressure and area, that's going to multiply to force. So let's try one of these. Let's go here. Actually, there. So here we have, the setup. Let's write down our formula. So here's how I would write it with the acronym. And the ADD mean essentially the same thing that they meant in the last problems. Acceleration, density, and here instead of distance, maybe you want to replace that idea with depth. Depth is distance from the surface, so you can think of it as distance anyway. It's just that it's distance from the surface. So that's going to be our acronym. That is going to give us force. This is going to work every time for these force problems. ADD is pressure, and then we have area. Pressure times area is force. Area now, we have to be careful. We're not talking about the area of the trapezoid. Just like the other problems we've seen, when we said volume in there, we weren't talking about the volume of the vessel. We were talking about the volume of a representative slice. So here, instead of slices, we have strips because it's just two-dimensional. So we just have strips across here. So when we say area, we mean the area of a strip. So here is a strip across here. And so we have to figure out the width here. And then the thickness of that strip is what builds it into area. And the thickness of this strip is dy. That is just a thin rectangle. Just like we did in the old problems where we were finding area. We're thinking of that as just a sleeping rectangle. It's very thin, dy. It's very thin. But that is the area we're talking about. We're talking about the area of that tiny blue strip right there. Not the area of the face. We're talking about a strip that's an integration element, and we want the area of that. So the area of that is just W times dy. So when we look at the area in this formula, this is what we mean. Just that. The dy is the thickness of that strip. All right. So this is similar to the trough problem, where we need the distance all the way across. So we can imagine the midpoint right here, and we can imagine a coordinate system if we like. And we want to find W. We want to find the distance all the way across. Well, what we are going to do is build the equation for this function right here. And that function is going to give us this distance, isn't it? That function, if we solve it for x, will give us the distance from the y-axis over to that curve. So that's our plan. Our plan is find the equation for this line here, solve it for x, and that's going to measure this distance across. So it's going to give us this x distance right there. And then how do we get W from x?
Multiply by 2.
Double it, yep. Right? Does everybody see that? So that is our game plan. That's our strategy. So we want to find the equation of this line. We know how to find the equation of a line with the point slope formula. So we do y minus y1 equals m times x minus x1. That is how you find the equation of a line. This point with the coordinate system that we've drawn is 5, 0. And if that's, so up here, that distance is 10 all the way to there. And if this is 5, what would the coordinates of this point be? 10, 15, right. I mean, another way to think of it, I guess, you just cut the 20 in half. That's going to be 10 that direction, and 15 is the y-coordinate. So now we've got our 2 points on a line. Point slope formula will do it for us. What point makes more sense? Should we pick that point or that point? We'll pick the one with the 0, right? Y minus 0 is a lot easier than y minus 15. Does it matter? No. You can pick any point. Does not matter. So we'll do the y minus 0, and then x minus 5. And then for slope, we just look here, and then our rise over our run. So the rise is 15, and the run is 5. Everyone agree with that? So there's the equation of the line. So we have y equals 3x minus 15. But we're trying to find a horizontal distance. Horizontal distances are given by x. So we are going to write this as an x value. So let's move the x's. Let's just translate, put the 15 with the y. Switch sides, put the x on the left. So this tells us that x is y divided by 3 plus 5. So that gives us half the width of the strip at height y. If we're not 100% sure that it's measuring what we want it to, let's check. When we plug in y equals 0, we should get 5. This half distance is 5. Sure enough, we plug in y equals 0, we get 5. When we come all the way to the top of this wall, the y value is 15 up there. When we plug in 15 there, we should get this half width distance, which is 10. Plug in 15. 15 divided by 3 is 5. 5 plus 5 is 10. So that's measuring the distance from the center line over to that right edge of the wall. This then tells us that the width of the strip at height y is 2y over 3 plus 10. We double it, multiply by 2. That will give us the width of the strip. That then tells us that our area is 2y over 3 plus 10 multiplied by dy. That is going to be the area of the strip at y. All right, any questions up to that point? Now we just have to throw it into our acronym and integrate. Any questions on any of the algebra? If no questions on algebra, we will go to calculus. So we are finding force. We are integrating. So we're finding the cumulative force. So we're looking at the force along each of these strips. And the limits of integration, we have representative elements from where to where? 0 to 15. We're using horizontal elements. And the water is all the way to the top based on the problem. OK, so our acronym, ADD area. So this is going to be the integral from 0 to 15. A is acceleration. Always going to be 9.8. The first D is density. The liquid behind this wall is water. Density of water is 1,000. And then D, distance or depth. So that second D, we're looking at how far down is this element of this strip. And how far down is it? Yeah, we're going to say that this is the horizontal strip at a height of y, so that y is representing that distance, which means this distance will be 15 minus y. So that is the distance below the surface, or the depth of the element, whichever your preference is. Okay, so there's ADD. Area is the width of the strip times the thickness of the strip. So now we toss in our last factor, 2y over 3 plus 10, and dy. So now we have all the pieces. Really similar to the pumping problems. It's just that we put an area instead of a volume at the end. And then like the pumping problems, almost all of them, we have a 9800 that we can just pull right to the front. And if we look over here, we could also pull out a 2, right? If we wanted to factor out a 2, we could factor out a 2. Doesn't matter. Let's pull it out. Let's factor out the 2. So we'll have a 2 times 9800. And then let's write down what we're left with in here, 15 minus y. And when a 2 is factored out, which was the doubling of the half width, we'll have that. Pretty straightforward integrand. We just FOIL and integrate with the power rule, so nothing crazy. So out in front, we're going to have 0, 0, 16, 18, 19, so 19,600. And then inside the integral, we'll do our FOILing. And let's write it in descending power, so we're going to have minus y squared over 3. We're going to have minus 5y. We're going to have what? Oh, do the inner and outer cancel? Bless you. So we have a minus 5y, but then don't we have a plus 5y? The inner and outer are going to cancel. That's convenient. And then the constants, 15 times 5 is 75. And that we can integrate pretty easily. So we have 19,600. Integrate the square term, we get minus y cubed over 9. And the inner and outer canceled, so then we have plus 75y. 0 to 15. We're going to have minus 15 cubed. And I see some 3's in there. I'm just going to write it really like I'm counting on my toes or something. Just write it like that. Because I can see that we're going to cancel a 3 here and make that a 5. And then cancel that 3 and make that a 5. Simplify it a little bit. Okay, and then we can just plug that in and get our final answer. So 75 multiplied by 15, and then subtract off 15 times 25. So that's going to give us 750 inside there. And then we're going to get a whole bunch of newtons. And I'm coming up with this many newtons. 14,700,000 newtons. So that is the important number that dictates how big the dam, how wide, how thick the dam needs to be to hold back all that water. All right, any questions on that? Oh, any questions on any of those steps?
Why is it just newtons and not square meters?
Because it's force. So we're finding force which has units of newtons. When we're pumping the water, that's work that's being done to move the water. So units of work are going to be Newton meters or joules, whatever your preference is. Force is just going to be newtons. And so if you look back at those two formulas, that's what the difference is right here. So we're going to end up with force because in here we have just area. But if we multiply by another dimension, in those problems, this is area of a strip. Multiply by another dimension, then area becomes volume, and then we have work. So force times distance would give us work. So from that work formula, we're essentially taking away 1 unit of length, which is going to turn it into force. Let's try another one. So here we have a triangular window in a pool type thing, or whatever, dam. Water's pushing on that. So once again, we're imagining a coordinate system right through the middle here. And the distance from the center over to that right edge is x. So we need to find the equation of this right edge and then solve it for x. And that will give us half the width of the strip. And we'll say that the strip is at a random y. So that strip is at y, a height of y, which tells us this distance is y, and this distance is 30 minus y. So there are our two distances. OK, the equation of a line, that should make you feel warm and fuzzy, the equation of a line. And this line goes right through the origin. So we don't even need to get as complicated as point slope. It goes right through the origin. The origin is 0, 0. So if you did it with point slope, you'd use y1 is 0 and x1 is 0. But for us, it's even simpler here. So all we need is the slope. Well, the rise is 30. The run is 10. So the slope is 3. That tells us if we solve for x that we have y divided by 3. That is the distance from the center line over to the right edge. That then tells us that the width of the strip is 2y over 3. We double it. All right. Now we're ready to write down our general formula. So force will be the integral of ADD area. That's what all we have to do is plug in the ADD and then find the area of our strip. So once again, 9.8. Once again, water, 1,000. So if we had a different liquid, if we had oil or something else, and the density would be different. If we had milk, whatever it is, have a different pressure, different density. Okay, so we've done acceleration, we've done density. Now we have to do distance or depth, and we just said that this strip. This representative strip is 30 minus y from the top. That's the depth, 30 minus y. 30 minus y. OK. Now we need area. And by area, we're talking about the area of that red strip. The area of that red strip, it's a sideways rectangle. All we do is multiply width times dy. That is the area of the strip. So right here, there's the width. 2y over 3. There's the thickness. That is what we mean by area. Length times width. And they say the water goes all the way to the top, so it's going to be 0 to 30. We have horizontal strips all the way from 0 up to 30. Any questions on that setup before we evaluate?
The 2y in your width, could you also take that 2 out to the front and call it a symmetry 2?
Absolutely. We could pull that 2 all the way to the front. We can also pull the 3 all the way out to the front because that's going to be a constant in the denominator. So that'll be our next step. Yeah, definitely. And we could always sort of think about pulling the 2 out instead of we could keep this as 2 times the width or 2 times y over 3 and pull it to the front every time for this. Yeah. Every single time. So out in front, we've got the 9800 again. And then the 2/3 is a constant as well. Constants just come right through the integral, just like they come through derivatives. And the only thing left in here is going to be 30y minus y squared. So we're going to distribute. The only thing left in here, we've got that and that. So we'll distribute the y across. Let's come over here, and let's just leave those constants alone for the moment, since 9800 is not divisible by 3. So this will be 15y squared minus y cubed over 3 from 0 up to 30. And then we'll plug in the 30. So we're going to get 15 multiplied by 900 minus, I'm going to write it this way. I'm going to take 2 of the 30s and multiply them together to get 900 and then leave one of them out in front. So the 3 goes into the 30, giving 10. So let's see if we can at least just write this down slightly simpler before we plug it into our calculator. So we have 15 900s minus 10 900s. That will give us 5 900s. So we have all that. Then we can plug it into our calculator. We could simplify it a little bit more first. 3's going to go into there 1. It's going to make that 300. So we can do a little bit of simplification before we plug it into our calculator if we want. That's going to be 10 times 300, which is 3,000. And that will be whatever we get there, which we should probably be able to do in our head also, since that's going to be 300 minus 6. 300 minus 6 is 294 with a bunch of zeros. And we're talking about newtons. All right. Someone double check that that's the right number of newtons. And let's examine anything that you're not 100% sure on. I feel like these applications, they sort of look a little ominous at first, but if you boil it down to the geometric pieces, none of them are that bad. The acronyms are both pretty easy: ADD area, ADD volume. And when we talk about volume, it's volume of a slice, not the volume of the whole tank. When we talk about area, it's the area of a strip, not the whole face area. Any piece of that that is not making sense? Any of the setup stuff you want to look at again? Or should we just do one more? These things, so we did the trapezoid, we've done a triangle, now we'll do a circle. So I tried to grab one of each of the types of shapes that we would see for our vessels and each of the type of shapes that we might see for a face, for a wall that has water pressing on it. So let's take a look at this one. So we have a diving pool, 4 meters deep. We've got a window at the bottom, circular window, radius is 1/2. We want to know the force pressing on this wall, on this window, on that window right there. Force pressing on that window. Okay. Coordinate system. Again, I always choose the coordinate system to be below the window or below the vessel. You could absolutely build your coordinate system right through the center of the circle if you wanted, but then your lower limit of integration is negative, which seems weird to me. I'd prefer the limits to start at 0 and go to the top, starting at 0. I love a limit of integration that's 0. Always is easier to manage. But it means the equation of our circle is a little bit more complex, but not that bad. We know that the equation of a circle in general is x minus h quantity squared plus y minus k quantity squared equals the radius squared. And hk is the center. So for us, the center is 0, 1/2, right? That's that point right there. The center of our circle is 0, 1/2. So that's why we have that equation. Once again, horizontal element at a random y. There's our horizontal element. We need x's. Horizontal distance deals with x. So we take our equation, we solve it for x. So I subtracted off the y squared thing, took the square root, and this right edge here is going to be the positive square root. So this is going to be x equals the positive square root. And what we'll do is FOIL that out. So let's FOIL it, and then we'll distribute the minus just to make sure that we are FOILing properly. So FOILing y squared. And then the inner is a times b times -2. A times b is 1/2 y. And if we multiply 1/2 y by -2, we end up with -y. Square the -1/2, and we get a 4th. So that is this distance right there. That's giving us half the width across the circle. It's giving us half the chord width. And we'll call the chord width W again. Width of that chord. Width of the strip. So W is 2 times that. And actually, I think no, I didn't write it there. But let's write it right here. So this tells us that W is 2 times the square root. And we'll simplify here. Coming in here, we see that the 1/4 are going to go away. We have a positive 1/4 and a negative 1/4. So we'll end up with -y squared plus y inside the root. So that is the width of our strip. The area of our strip, multiply that by dy. And that will be the area of the strip. OK. Oh, yeah, and I did it in here anyway, but we'll do it from scratch. So we are trying to find force. And our acronym, we are going to use ADD, area. So now that we've talked about this is pressure. Force is pressure times area. Gives us another way. Yeah, ADD is pressure. It's another way to think of that inside. So for us, in this particular example, integral 9.8, acceleration due to gravity. Magnitude of acceleration due to gravity. Density, water. Density is 1,000. Distance or depth. By that we mean the distance or depth for this element right here. How deep is that? 4 minus y. Right, the full pool is 4. This distance right here is y. This distance right here is 4. So the depth is right here, and that will be 4 minus y. And then area of the strip is the width of the strip multiplied by dy. And the limits of integration, 0 to 1. There are strips of water pressing on this window from 0 up to 1. The radius of the circle is 1/2. So the diameter of the circle is 1. So we have all these strips of water that have force. We're going to try to figure out the cumulative force. And notice also, this is interesting, like the water up here matters, even though this water is not physically touching the window, that water matters. Right? That water is increasing the hydrostatic pressure down here. So the pressure pushing on the window depends on how much water is above it, not just the water right in front of the window. So we have to integrate all the way to the top, from the top. Or the distance. This is the factor that matters there. Right? That gives us, that includes the water above. Okay, so again, we have a 9800. And we have a 2 that comes out. And let's write what's left. This one's going to be a slightly trickier integral. This, well, let's write it down first, then we'll talk about the nature of it. Okay, so that's what we have. Now, we saw an integral recently that looked a lot like this. Typically, we go with substitution. And when we go with substitution, we use u equal to usually what's in the square root. That's going to be the natural thing to do. Because we can't break this square root into the square root of minus y squared plus the square root of y. So the problem, sort of the piece that we can't break apart is that. But if we put a u in there, then the square root of u, that's a good thing. Then we have one term, one factor inside that square root. That's our goal. Because we can't break this apart. So if we could let u be that, then we'll be in business, usually. So we're going to let u be minus y squared plus y. And then we do the whole derivative differential thing. The derivative over here is minus 2y plus 1 and multiply by dy. And that's not matching what's in front. So here's where we're going to have to be clever. This is a little more clever than what I would put on an exam. This is going to take us a little bit more ingenuity. So we saw with the trough that when we let u be the guts of the root, its derivative matched what was in front. So it just unraveled very easily because everything matched. We took the derivative and it matched. Here, that's not happening. So let's investigate a method or a strategy that will help us here. Okay, so let's simplify that. And inside here, we need to think about what we can do. So the first thing I notice is that we have a negative 2y there, and here we just have a negative y. So that's a problem. And here's what I'm going to do to rectify that problem. I'm going to multiply by 2 right here. And I'm going to multiply by 2 because I want to force that to be a negative 2y. All right. Well, if I multiply by 2, I also have to divide by 2. We need to keep the balance, right? We need to keep the balance. So we're going to toss, and I multiplied that 2 in. I shouldn't have multiplied that 2 in. So now we do that, right? Haven't changed. All we've done is change the look, not the value. All right. Now, so let's see. That's going to go back to 9800. And in here, we're going to have 8 minus 2y. So we're getting a little closer. Getting a wee bit closer. Well, we want a negative 2y plus 1. We know how to rewrite 8. We can rewrite 8 as 7 plus 1. So let's write it as 7 plus 1 minus 2y. We can do that. No problem there. All we did was rewrite 8 as sum of two numbers. All right. So that's looking a lot better. So now, this right here, we can write this in any order we want. Right? Commutative law of addition, we can just change that. So now what we see is a match right there. There we have a match. So what we are going to do is now rewrite this single integral into two separate integrals. What we are going to do is distribute this integral, this square root. We're going to distribute it to this yellow and then over to the 7. All right, we can distribute. So let's see what happens. So we're going to distribute, getting 9800ths. That's way out in front. I'm going to put a big bracket here because we're going to have two integrals in here. We're going to have 7 multiplied by the integral from 0 to 1 of negative y squared plus y dy, plus the second integral from 0 to 1 is going to have a 1 minus 2y in front of the square root. Okay. The second integral, u sub, is going to work beautifully. This is u to the 1/2. Right? The u is that, so that's u to the 1/2. And this whole thing here is du. This whole thing is just u to the 1/2 du. And we have to convert to u limits. What would the u limits be? How are we going to get u limits? So right now, the y limits are 0 and 1. What are the u limits? Say it louder.
0 and 0.
0 and 0. Beautiful. 0 and 0? What does that give us? 0. So this whole thing is just going to give us no contribution. Perfect. We like that. And then over here, the only thing that's left is this. All right. Now we have to figure out what this means. All right, so that's all 0. Integral from 0 to 0, nothing. Now this is not integrable by using normal substitution methods. But we know the geometry of this integral. We know that a definite integral measures the area beneath a curve. And if it's a function of y instead of a function of x, it means between the curve and the y-axis. So if it's functions of x, then it's below the curve and above the x-axis. If it's functions of y, it's between the curve and the y-axis. So we just have to understand the geometry of this. This is a function. What function is it? OK, it's x equals this. And we're just going to go back to where we were. What function is that? I don't know. Square both sides, add the y's, subtract the y, equals 0. So squaring both sides, putting the y's all on the left, add y squared, subtract y. So just move everything to the left. Complete the square, divide this by 2 and square it. So we add a quarter to both sides. And we're just going right back to where we were a few minutes back. So this is x squared plus y minus a half squared equals 1/4. Right, that's where we started from originally. That is that circle right there. That's the equation of the circle wherever we had it, right there. Right, so we're back to the original circle. So this is the right half. And we usually would say the right half is called a semicircle. So right semicircle. Everyone agree with that? So that is the right semicircle of radius 1/2. So if we were to draw this thing, okay, so let's just draw that. This is radius 1/4. Excuse me, radius 1/2. So what portion of this? So this is the right half of the semicircle. This would be negative 1/2 down here. This would be positive 1/2 right there. There's x equals 1/2. There's x equals negative 1/2. If the x values are going, oh, I didn't, so let me just make the coordinate system look better. That was terrible. That was terrible. What's the center of our circle? 0, 1/2. Thank you, right here. So that's 0, 1/2. So the coordinate system we're envisioning is down here. There's the coordinate system. OK, so if we're integrating from 0 to 1, this point up here is 0, 1. We don't care about those points, really, because we're integrating this way. So what does the integral represent, then? So we want the area between this curve and the y-axis from 0 to 1. Here is a picture of the curve. Do the limits give us the full semicircle or just part of the semicircle? Say again? So let's think about where these limits are. So 0 is down here, and we're going all the way up to 1. We're finding the area between the curve and the y-axis all the way from 0 up to 1. So we are getting the full semicircle. Full semicircle. So because these limits are 0 to 1, this gets us all the way across the diameter, because the diameter of the circle is 1, since the radius is 1/2. So if these limits went from 0 to 1/2, we would only get 1/4 of the circle or half the semicircle. If the limits went from 1/2 up to 1, then we get this top quarter. But this integral in general is measuring the area to the left of this curve from 0 to 1. The curve is right here. 0 to 1 is that whole distance, so we're going to get the whole semicircle. And the area of a semicircle, we know that the area here, the area of a semicircle, is going to be 1/2 the area of the full circle. So it's 1/2 times pi times the radius squared. The radius is 1/2. So the area of this semicircle is pi divided by 8. And so that is how we can finish this one off. That is definitely a little harder than what I would put on an exam, but it's something you should be able to follow. And then whatever that is, 7/8 of 9,800. $85.75 times pi newtons. OK, let's go over any questions you might have from any of the crazy steps there. So first off, let's go back to the setup and make sure. So we started with the circle centered at 0, 1/2. Is there any questions on finding the equation of the circle or finding the width of a strip or any of that original stuff from the beginning? On the exam, if there's equations of circles, I'll try not to put fractions in them, because I know that that just complicates it even more. Even though, like if you don't feel any ADD, if you don't feel any pressure, maybe fractions don't matter, but in a testing situation, that pressure can feel a little bit more than is necessary. So if there's circles, I'll try to make the radius an integer, not a fraction. Other following the substitution in, acceleration, density, depth, area means area of this tiny rectangle. Bummer integration here because the u's derivative doesn't match what's in front, so we just creatively said let's separate. Let's make it match part of it and see if we get lucky. Say that once again. Explain.
That part.
The 4 minus y?
Yeah, because it's not part of the. Because we're looking at the circle. And
So the water, so the pressure, so if you imagine being at the bottom of a swimming pool, right? If you go all the way to the bottom, you're feeling just as much pressure right here as you are right here.
Right.
So the water does not have to be in front of you. You don't need, the water above you is what creates the pressure that's pushing on you here.
Right.
So it's not, so this water right here is contributing to the pressure pushing there, even though this water feels like it should only be pressing there, but it's creating a weight, it's creating a force down here that increases the pressure, so the pressure pushing on this wall does depend, or this window, does depend on all the water above it. So this water counts, even though it's not pressing right against the window.
Right, so it counts for the distance,
Mm-hmm.
not the area.
Correct.
Looking at the surface.
So it counts for the distance the water is below the surface, but it doesn't increase our limits of integration. The limits of integration are where the actual strips are that are putting pressure on the wall, on the window. On the window.
So,
Other ones?
yeah, so basically we're trying to find y here.
All right, let's take our 10-minute break, and if you have questions on this, let's go over them during the break. Or if you have other questions, you can bring them up during the break. Figure out what we need to know. So some of this preliminary stuff, you're not going to be tested on. This is just sort of the background of hyperbolics. All you're really going to be tested on are derivatives and integrals of the hyperbolics. But there's a couple of slides that give you some insight into why we call them hyperbolic trig functions. So they're related to the trigonometric functions for very, very important reasons. So first off, let's go back to the unit circle for a minute. And the unit circle is where we define the 6 trigonometric functions. They're also called the circular functions because they're coming from that circle. And when we look at a unit circle, we know that the x value is cosine as a coordinate on the unit circle, and the y value is sine. And we also have a really important formula that relates arc length to the angle and the radius. Anyone remember what that formula is? It's not a formula you'll need for the test, but anyone remember?
Is it like theta r?
Yes, yes. S is equal to r theta. So again, that's a formula that will come up from time to time. It's not one that most people, you're not usually asked to remember that. The way I remember it is if you look at your theta, if you put your circle in, if you put your sector in standard position, there's S, there's R. The way I tend to think of it is that, and I want to put that R on the bottom, is that it looks a heck of a lot like slope. Right? Theta is S divided by R. It's the circular rise divided by the run or the radius. So it's a lot like that. That's one way that you can remember it. And one important thing is that in calculus, we use radians for a reason. The reason is that they're unitless. If you're using degrees and you're taking derivatives and things, then you need a chain rule. Because a degree is a fraction of a radian. Like, you have to do a conversion to get from radians to degrees. These formulas like derivative of sine is cosine, those are all based on using radians. And because radians are unitless. If you look here, S, that's a distance. R is a distance. The units cancel, so you get a unitless number. So it's kind of like slope. When we say slope, usually we think of that as unitless. Right? We think of the rise and the run as having the same units, and so slope is unitless. So it's that idea. So we like to have radians because that means that we're not dealing with units of degrees. When we say radians, it just means not degrees. That's really what that means. Right? Okay, so if we're on a unit circle, that's an R. So if we're on a unit circle, the radius just disappears. And theta and S are the same. And this is why you hear arc sine. Because the focus in the old days was on the arc more than the angle. But they're equal. The arc and the angle are the same when you're on a unit circle. So when you see arc sine of 1/2, we say the angle that has a sine of 1/2, whereas in the old days, they would say the arc that has a sine of 1/2. Their focus in the old days was more on the arc instead of the angle. So that's why they use the word arc sine instead of just inverse sine. So one thing we notice here, we also have a formula for area, and area is 1/2 theta r squared. If we're on a unit circle, then what we're going to have is, so if r is 1, then this is going to be a equals 1/2 theta, or theta equals 2a, however you want to write it. And if you look here, so the area right there is going to be, in this case, in this picture, they're using t for the angle. So you would have that area is t divided by 2. So that's going to be the area of a sector. And that's going to be the weird connection with the hyperbolics. So here is a picture of the unit hyperbola, the right half of the unit hyperbola. And we're going to do the same type of thing. We're going to take our point on the curve and go over to the origin. And there's an area. There's the hyperbolic area. Sometimes it's referred to as a hyperbolic sector. So this is a circular sector. That's a hyperbolic sector. And the connection is that area matches this. So t, or the angle. Now, in a circular picture, you can see the angle. With the hyperbolics, you don't have the same visual for the hyperbolic angle. We don't see t on this graph like you see t with circles. But the value t right there, that is going to give you twice the area of this sector right there. So that is one of the connections between the unit circle and the unit hyperbola, is that those two areas are both found in the same way. Okay. All right, so there's the hyperbolic, the unit hyperbola that we use to define these functions. And instead of sine and cosine, we're going to use cosh and sinh. So there's no standard pronunciation for a lot of these things. Some people will call this cosh instead of cosh. Doesn't matter. Sinh, though, most everybody calls sinh and cosh, or sinh and cosh. Sinh is pretty standard. So here are the other ones. So there are 6, and they are going to be, we're going to have the standard representations for these 4 down here, like tangent is sine over cosine. For the hyperbolic tangent, which most people will call tanh, tanh will be sinh over cosh. So very similar. Tangent is sine over cosine. Tanh is sinh over cosh. Hyperbolic secant, a lot of people call it sech. Sech will be 1 over cosh, just like secant is 1 over cosine. So the big parallels here. Cotang, the hyperbolic cotangent. Cotang, cosh over sinh, just the reciprocal of tanh. Same as in tangent and cotangent. That's all lined up perfectly. And the same for the hyperbolic cosecant, which we usually call cosech. So we have sech and cosech, tanh and cotang, and some people will say sinh and cosinh, or sinh and cosh, whatever. They're used so infrequently that there's just not a uniform agreement to what we should call these things. So you'll hear different things. Now this is fascinating. Cosh, by definition, and sinh by definition, are defined with the exponential function. Now that seems like a big difference from sine and cosine. You've never seen sine and cosine, most likely, written in terms of exponential functions. When we get to power series, which are infinite polynomials, you will see, actually, that the sine and cosine and the exponential function do have a really, really important connection. You just haven't seen it yet, because it takes infinite series in order to see the connection. But with the hyperbolics, the connection is really apparent. It's right here in the definition. I am not so interested in going over to these definitions in terms of the exponentials. That's not a focus for us. You will see it in some of the homework questions, but that won't be on the test. We're more interested in derivatives and integrals. But in the homework, you might see convert this over to convert this over to exponentials, and these are the two relationships. Let's pass on that for a second. Let's just go to this slide, because it's really important to understand this cosh function. So that definition says that cosh is going to be the average. Let's put a t there. So it's e to the t. Did they use a t or an x? Does not matter, obviously. So that's cosh of t. It is the average of exponential growth and exponential decay. Right? E to the t goes like this. E to the minus t goes the other way, so they crisscross like that. So growth, decay, average, that's cosh. So, and this is always positive, right? When you look at that, positive number, positive number, positive number, that can never be negative. So its graph is above the x-axis, and this is the graph of cosh, right there. So it is the average of exponential growth and exponential decay. This is the most important hyperbolic function. And I have a video up there in the discussions that you should look at. This is sometimes called the catenary. And that function is important if you know anything about the catenary. And there's all sorts of great videos on the catenary. And it has a bunch of really interesting properties. This is, if you ever watched Mythbusters, those guys, and Vsauce, who does a bunch of really cool math videos, those guys do all sorts of fun stuff with the catenary. So some of the properties that the catenary has, if you take if you take a ball right here and a ball right here, well, let's put the ball on this side. So one there and one there, they will meet at the bottom at the exact same moment. So they call it, I think that property is called a tautochrone, because it takes the same time to get to the bottom regardless of where you drop the ball. It is also, I think the word is brachistochrone. That is the, maybe you have the two words backwards, a brachistochrone and a tautochrone. One of them is that the time it takes is the same no matter where you drop the ball. The other is that it's the fastest possible way to get from this point to this point. Right? There's a million different curves that you could imagine connecting those two blue dots. And the catenary is the one that has the fastest rate to get from there to there with the ball. So you can draw a straight line, you can do all these things. And which one of the Mythbuster guys connects with Vsauce and does those things together?
Adam Savage.
Adam Savage. So he and Vsauce did this great, they built models with ramps and huge sizes with a bazillion different curves, and they empirically measured to show that the catenary was going to give you the fastest distance, the fastest time for a released ball on the fastest slope. So that's pretty cool. It is also, if you flip it upside down, it is the most stable arch. It is the arch that can hold its own weight. So if you look at that St. Louis arch, that's just an upside down catenary. That is going to give you the strongest way to build an arch, if that's your thing, building arches. The other curve, the cinch, is going to look a heck of a lot like x cubed. It looks a lot like x cubed, except there's going to be this other property of it. It's not x cubed, obviously, but it looks a lot like it. But it is going to approach, it's going to asymptotically approach the exponential growth function right here. And the cinch and the cosh are going to approach that curve. The cinch and the cosh will never meet. They don't intersect. But that's what the graphs look like. Cinch can obviously be negative. Cosh is always positive. So that is where they come from. Averaging the exponential growth and exponential decay. So let's take a look at the properties here. These are all going to be very similar to what you know about trig functions. I'm not interested in most of them. So this is the fundamental identity. That's like the parallel to the Pythagorean identity. Instead of sine squared plus cosine squared is 1, it's cos squared minus sinh squared is 1 from a hyperbola. So cos squared minus sinh squared is 1. And you just have to remember that cos comes first. Well, if you have the visual that cos is that hanging cable and sinh is below it, that's got to come first or you would get a negative number. So if you look at that graph, right, if we were to do the subtraction here, the only way we can subtract these and get a positive number is if we do this one on this one first. Cos has to come first. So it's got to be cos squared minus sinh squared is 1. So that one's very important. These two you should be able to get from that one the same way you get the other two trig identities by dividing. We can talk about the details of that when we get to it. These are the odd-even properties. Not interested in those. But this tells us, as a reminder, that the cos is even, because if you plug in negative x or x, you have the same y value. That's what even means, symmetric about the y-axis. Whether you go positive or negative, same distance, you have the same y value. That's even. This says sinh is odd because, so that's even, that's odd, because if you go to x, you go to negative x, you go opposite directions. All right, so that's what odd is. And then that one is odd also. But you're not gonna have any questions on that. Sum and difference identities, we're not going to look at those, but they parallel the sum and difference identities. The double angles, we're not going to look at those, but they parallel the double angles for the trig functions. And then these are power reduction. So I'm not going to ask you to memorize or any of these things here. On a homework, you might see something where you have to come and look at this and say, oh, to integrate cos squared, I need to do this. Or to integrate sinh squared, I need to do this. But for the exam, you do not have to memorize any of those identities. This is a good one to know, though, because we're going to use that one a fair amount. Or the most of all of them, that one. But the focus is, again, on derivatives and integrals. So let's look at those. OK, so we're going to have to come up with a way. There's going to be some slight differences. With the trig functions, usually what most people remember is that all the co-functions are negative when you differentiate them. Right? They all turn into negatives. So if we look at the derivative of cosine, that's negative sine. If we look at the derivative of cosecant, I can't even write cosecant, that is minus cosecant cotangent. And if we look at the derivative of cotangent, that is minus cosecant squared. So usually with the trig functions, you remember sine, secant, and tangent. Derivative is positive, but the three cos are all negative. So we need a different sort of memory trick here. So what's cool is that the derivative of cos is sinh and the derivative of sinh is cos. No minus to remember. Okay? And then when we get to tangent, the derivative is sec squared, which looks a lot like the derivative of tangent. The derivative of tangent is secant squared. So the thing in my mind here is that the primaries, so with trig functions, the primaries are sine, cosine, and tangent. The primaries for the hyperbolics are sinh, cos, and tangent. And the primaries all have positive derivatives. Right, those are the ones we primarily look at, sine, cosine, tangent. Similar for the hyperbolics, sinh, cos, and tangent. Those are the ones we primarily look at. Those are all positive, and then the others are all negative. So cotangent, negative, sec, negative, cosec, negative. So you just have to somehow orient that in your mind, which one is which. And just like we know from Calc 1, anytime we have a derivative formula, we have a corresponding integral formula. Derivative of cos and sinh are each other, so the integrals are each other. All right, so that part's the easy part. And then we just have to remember the signs for all these other ones. You know, integral of sec squared is tangent. Integral of cosec squared, the minus comes over here and gives us minus cotangent. The integral of sec-tangent, the minus comes over and gives us a minus sec. Integral of this one gives us a minus cosec. OK, so basic derivatives and integrals. Down here, the two that are going to be important are these two, and these two we will not look at. Those two antiderivatives are crazy. These ones, we're going to come up with very simple ways to look at those. All right. Let's do some. Whoops. All right. So just like with the trig functions in Calc 1, you started by showing the derivative of sine was cosine and the derivative of cosine was minus sine. You did it with limits. And once you got to that fact that you knew the derivative of sine and cosine, then you could find all the other derivatives with the product rule, the quotient rule, or whatever. So same idea here. We're going to use these two basic facts, derivative of cosh is sinh, derivative of sinh is cosh. We're going to use that to show the other ones. So if you happen to forget where the sign is, the minuses, you could do this. So we know that sech is just 1 over cosh. So we've got that parallel relationship just like the trig functions. So you could replace sech with 1 over cosh. And then use the quotient rule. So we're going to do low times d high. And what's the derivative of the numerator? 0. So low d high minus high d low. And we use that fact up here. The derivatives of sinh and cosh are each other. No minuses to worry about. So low d high minus high d low. So we're going to put a sinh right there, divided by low squared. And then we're almost there. So we end up with, we're going to pair off this sinh with one of those coshes. And then we'll leave the reciprocal of cosh as the second factor. And that gives it to us. 1 over cosh is sech. And sinh over cosh is tanch. So this gives us, if we write it in the same exact order, we would write it as minus sech tanch. So we can use those two basic facts to get the derivatives of all the other 4. You all work on that second one while I take roll. So find the derivative of cosech using the quotient rule. Charbel. Ray. Skylar Brady, not here. Federico. Logan. Raquel, Jack, Be Fresh is not here. Tim, do you have 2 Tims? Tim Hoyt. Yeah, you are here. And Linda, and Nick, Patrick, here, Brady, here. Tabitha, here. Jesus, here. Anastasia, here. Connor, here. Hannah. Cameron. And Ryan Rodriguez, not here. He's usually over there. Elijah. Brandon, Oliver, Skylar, Tyler.
Right here.
Yep. TT. Did you say your last name?
Tout.
And then Tim, Daniel, Ryan Tran. And then Peyton's here. Alyssa. And Bradley. Bradley has not been here for... Oh, were you here last time? I think so. But you're here now. Okay. Any issues? A little bit less sort of brain drain than all the applications in 6-7 for sure. So our strategy is just to use the quotient rule. So we're going to write cosec as a fraction, 1 over sinh, and then we'll use the quotient rule. So we're going to do low d high, low function multiplied by the derivative of the upper function, the high function, 0, low d high, minus high, which is 1, d low is cosh, divided by low squared. So in the numerator, just like in the numerator above, we had a term that went to 0. And then we're just going to parse that denominator. We're going to make a 1 over sinh and a cosh over sinh. And 1 over sinh is cosec of x. Cosh over sinh is cotanch. Yeah, so parallel to what you did in trig and calc 1. Once you have the two basic derivatives, all the other ones just follow like dominoes. Chain rule. Chain rule. Let's rewrite this with a 1/2 power. Usually it's a little easier to do the power rule if you have, write it with a fractional exponent. So same thing that we normally would do. So to find the derivative, we're going to bring down the power, subtract 1 from the exponent, and then take the derivative of the inside. So this is going to be 1/2. And then the base of this expression stays the same. Then we subtract 1. And now we have to multiply by the derivative of cotanch. So the first thing we probably think about is the derivative of cotangent is minus cosecant squared. So this parallel would be minus cosec squared. And then we just want to make sure that we have the minus sign correct. So with the hyperbolics, sinh, cosh, tanh all have positive derivatives. The others all have negative, so we do keep the negative. So we're going to have negative cosec squared of 3x. And then chain rule again, multiply by 3. And if we simplify this, looks like we're going to have minus 3 cosec squared of 3x in the numerator, and then in the denominator 2 times the square root of cotanch 3x. So that's one way to simplify it. You could turn everything to sinh and coshes also, but they don't ask us to, so let's not do it. Any piece there? So this really just is a little bit of practice. Make some note cards, make sure you get the derivatives and integrals down, and then we're just doing Calc 1 stuff again. Derivative here, the derivative of a log function is 1 over the inside multiplied by the derivative of the inside. So 1 over the inside. Derivative of sec, that is not one of our primary 3. It's not a sinh, cosh, or tanh. So that means the derivative will be negative. It's going to have a negative in it. So it's going to be negative. And it's going to parallel when we take the derivative of secant. We get secant times tangent. Parallel, sec, tanh. So we're going to have a sech of 2x times a tanh of 2x. And now the derivative, again, inside that function is 2. So then we're going to have a multiply by 2. Simplifying here, we get the sech's canceling, and it looks like minus 2 tanh of, oh, these should have 2 x's in them, not just x's. Oh, they do. Oh, that one does. This one doesn't. I need a 2x in there, not just x. So that is our derivative. Product rule. You all try that one. I'm assuming you can remember the product, that you remember it. If not, we'll do a little more practice. So product rule, we're going to treat that as the first function, that as the second function. So see if you can pull that one out of the cobwebs. Any issues? I guess we'll find out, right? So first derivative second. First derivative second. Derivative of tanh, okay, that's a primary one. Sinh cosh tanh primary, so that means the derivative will be positive. And then it parallels. Derivative of tangent is secant squared. So derivative of tanh, sech squared. Sech squared x. First derivative, second, plus the derivative of the first times the second. Derivative of first times the second. Is that the form of the product rule that you all use, first derivative second plus derivative first second? Or do you do second derivative first? Do it the first way I said it? Good. That's important because in Calc 3, when you're doing derivatives or product rule for vector valued functions, it has to be first derivative second plus derivative first times second. The commutative law does not work with vectors. In certain contexts, it does not work. So it's important to practice it now in that order, because that order is what's going to persist. Okay, so that is our derivative there. Another product rule here. So this one is going to be first function. Derivative of second, we have a bunch of stuff going on. Sometimes folks want to rewrite this like this to keep it clear, put the square on the outside. The trig functions are the one function that we always have the square kind of not on the outside. Although this book, as you start to look, is the first time I've ever seen this in a textbook. It's kind of interesting and it makes sense. Up until recently, if you wanted to square natural log, you always wrote it like that. This book, again, first book I've ever seen, will write it like that. which parallels what we do with trig functions. It makes sense. But you just have to remember that that's on the outside. So when we come here to take the derivative, it's 2 cosh 3x. Now we subtract 1. So cosh 3x to the 1. Now we differentiate the base. Derivative of cosh is sinh. And then we differentiate the angle. So that is first derivative second, plus the derivative of first multiplied by second. A little bit of stuff we can do there. So we'll have 6x squared cosh 3x sinh 3x plus 6x squared. No, that's inside. So 2x, that one is, it is what it is. Oh, wait, put a 6 again. Just a 2. Any issues with chain rule, product rule? All coming back? Yeah. Good, good, good. All right. Okay. Let me just check one thing. I want to make sure I don't repeat myself. Okay. So let's add a slide here. I want to look at a couple of things. So the two integrals I said would be important were the tangent and the cosh. And I want to show you examples of these. The tangent and the cotangent, I mean to say. Tangent and cotangent. I want you to be aware that these are both accessible if we turn these if we turn the insides into their quotients. So tangent is going to be sinh over cosh. And cotangent is going to be cosh over sinh. What form are both these integrals in? Log form. Those are both in log form. Remember that log form is when the derivative of the denominator is identically the numerator. And when the derivative of the denominator is identically the numerator, we're done. It's natural log of the absolute value of the denominator. That is how we integrate something in log form. Do we need the absolute value on a cosh? No, because cosh is the hanging cable. Cosh is the hanging cable. It's above the x-axis. So we don't, is it okay to put it in? Sure. It's not going to hurt anything. But you don't need it for a cosh. And because the derivative of sinh and cosh are each other, this one is also in log form. We don't have any minus sign to deal with. We just take the absolute value of the denominator. This one we definitely need the absolute value because sinh can be negative. And log functions are only defined for non-negative numbers. Actually, logs are only defined for positive numbers. They're not defined for 0. So positive numbers. So we need the absolute value. Good? Doesn't feel quite as dramatic as physics applications. Okay, so let's get to slightly more complicated scenarios. We've got some products of trig functions, some quotients of hyperbolic functions. And they don't have immediate antiderivatives. Like we don't know a function that has tanh sech squared as its derivative. So the only technique you really know is substitution. Right? That's your technique. So what do you think might happen? Let's see. If we are going to use substitution, we've got 3 choices. We could let u be tanh. We could let u be sech. We could let u be sech squared. Letting u be sech squared seems kind of dumb, though, because the derivative of sech squared, we'd have 2 times sech to the 1 times the derivative of sech. Like, that's going to get pretty gnarly. So we have 2 practical ones. What is the derivative of tanh? Right there, right? So that makes perfect sense. If we let u be tanh, then its derivative is part of the integrand. So that is what makes u substitution work. If the derivative of whatever you let u equal is part of the integrand, then you're most likely on the right track. So this is going to become the integral of u du. So u is tanh. Du is sech squared of x times dx. That's the entire thing. And the integral here, we'll just get u squared over 2 plus c. We back substitute, so we're going to have 1/2 tanh squared of x plus c. Yeah?
Where did the x go? Because we have sech squared x tanh x dx.
Mm-hmm.
Where did our x go?
So this x is inside, right? This x is inside tanh. This x is inside. This x is inside sech. This x is inside tanh. You see it?
Okay,
Yeah.
yeah. Okay.
There's so many letters, it starts to look
Yeah.
a little bit jumbly.
Okay, yeah.
Putting parentheses around the hyperbolic angle is not a bad idea, but most of the time people don't do it. Even though it just starts looking like alphabet soup. It's like 5 letters. What? Okay, so similarly here, let's see. Can anyone see the answer right without writing anything down? I claim you should. Jack?
The natural log of the absolute value of 1 plus cosh.
Yep, that's right. Isn't that in log form? Right? The derivative of that denominator is sinh. The derivative of 1 is 0. The derivative of cosh is sinh. So that is in log form. So we can write down the answer immediately. It's natural log of the absolute value of the denominator plus c. And then here, once again, we say, oh, cosh, you don't actually even need the absolute value because cosh is always positive. So you don't need the absolute value. It doesn't hurt to have it. I wouldn't mark you off for it. It's still correct, but you could simplify it a little bit. So log form, super important, always. Can always cut to the chase. It doesn't matter though if you did u equals, this would also work if you didn't notice that right away. If you were going to do substitution, usually inside the square root, inside the angle, in the denominator, in the exponent, you sort of grab the part of the inside that is the worst. And so if we let that be u and we took our derivative here, you sure enough see that you would get the integral of du over u, which is natural log of u. Plug that in, put your integration constant, and get the same thing. Does not matter. Doesn't matter. Okay, again, we're looking at substitution since we don't have an antiderivative that's jumping out at us. Don't have an antiderivative jumping out at us, let's go with u sub. So what we're trying to do is let u be something so that its derivative is in the integrand. And we don't want to let u be a square, because then we have chain rule and power rule all mashed together and you get some gnarly looking thing. So when I look at this, the 2 candidates are cotanh or cosech. Let u be one of them. Do we have a choice? One of them is going to work a lot better than the other. What is the derivative of cotang? Right, minus cosec squared. And there's a cosec squared. So that lines up really well. So if we let u be cotang of x, so this is not one of the primary three, not sinh, cosh, or tan, so its derivative will be negative. And then it's going to be negative, and it's going to parallel the derivative of cotangent, which is minus cosecant squared. So this is minus cosec squared times dx. And so this fits in very well. We let u be cotang, so inside we're going to have a u squared. There's the cotang squared. And then cosec squared times dx is minus du. So we'll put the minus out in front and put a du. So this will be minus 1/3 u cubed plus c, which will be minus 1/3. U is cotang. And that will be the antiderivative. Let's do it. Let's shut them out. Thank you. Any questions on that one? All right. So just like sine squared and cosine squared can't be integrated immediately because they don't have antiderivatives that we know, what we had to do with sine squared and cosine squared, you had one example of that in the homework, you had to use a power reduction identity. And so that is true for sinh squared and cosh squared also. We would need a power reduction identity. We need to somehow reduce this power down to 1. And so we had our power reduction identities for sine squared and cosine squared, and there are parallel ones. Again, I'm not going to ask you to memorize them. So there are parallel ones for these. So our power reduction identity is right there. So it looks almost identical to sine squared. It's just that the numerator is reversed. That's the only difference. So that is going to be our trick. Not a trick. That's going to be our strategy. So we're going to rewrite this as the integral. So we have a 1/2. And sinh squared is 1 minus cosine of 2x. This is just going to be reversed. So it's going to be cosh 2x minus 1 dx. The 2 in the denominator can come out to the front. So you can kind of do this in a couple different ways. So let's just get that out of the way first. So just like with the power reduction for sine squared and cosine squared, as you reduce the power, you increase the angle. So now the angle is a double angle, which means RCR. This is linear. And whenever we have a linear inside, we are thinking reverse chain rule. You could use substitution. It would work. But it's unnecessary. So integral of cosh is sinh. So we're going to have sinh of 2x. But then the reverse chain rule, what do we have to, how do we modify that? Divide by 2. Perfecto. And then the integral of 1 is just x. And then we have our integration constant. And typically, leaving it in this form is kind of silly because you have part of it factored, which is not helpful. So usually the answer you would see in the answer key or whatever would normally be that. Good? All right. Final slide. It doesn't look like a kiln to me, but they're calling it a kiln. Find the volume interior to this inverted catenary kiln shown in the figure. So here is the entrance there. And we want to find the volume of this. So to find the volume of that kiln, really what they're asking us to do is to find the area of this face and then multiply it by 6. That's how we would find the volume. So if we find the area of the face, multiply it by the length, that'll give it to us. So what we're trying to find then is the area of the face, the area of the entrance is going to be the integral of the curve that represents the face. So integral of this. Now, okay, to find those limits of integration, we would need to know what these 2 points are. So we want to know, well, where is our function equal to 0? That's what we're trying to solve. All right, so we isolate the variable term. We have that. The only cosh value we know is cosh of 0 is 1. The hanging cable goes right through 0, 1. We have no clue where the hanging cable is equal to 3. So all we can do here is say that x is going to be equal to the inverse cosh of 3. That's all we can do. That right there. So this says this is going to be equal to the, in trig terms we would say angle, right? So here we might say hyperbolic angle, but when you say angle, all of a sudden you start thinking about rotation. Remember that a hyperbolic angle is not a rotation counterclockwise like a regular angle. So it's the hyperbolic angle that has a cosh value of 3. So that's all we know. So what we would do is come over here to our integral. Do you see that we could use symmetry? We could go from 0 to inverse cosh of 3 and then double it. Does that make sense to everybody? Okay, so we can in fact do the integral part. That's not too difficult. We get 3x. The integral of cosh is sinh. And then we're going to go 0 to inverse cosh of 3. Plugging in 0 is going to give 0. 0 here obviously is 0. 3 times 0 is 0. Sinh of 0 is 0. That's the only value we know for sinh. We know that sinh passes through the origin, and we know that cosh passes through 0, 1. So those are the only, we only know one value for each of them. But at least with 0, we know we have nothing there. So we are going to end up with, let's distribute the two in one step. So we're going to have 6x, so we're plugging in that. So it's 6 times inverse cosh of 3, minus sinh of inverse cosh of 3. That is our exact answer. For the area of the face. Then we'll multiply by 6 to get the volume. Yeah? Oh, maybe. 100%. Tim, is that what you were going to say?
No, I was asking about the multiplying by the...
Oh, multiplying by the 6. Yeah. So this will be the area. And then the volume, we'll multiply that by 6. Now, if it says get an approximation, if we wanted an approximation for this, which is probably what they would ask, we can, oh, I didn't pull up Desmos yet. We can just do this in Desmos. You know, Desmos is great to get approximations. It's great to check stuff. So 6 cosh inverse 3 minus 2 sinh parentheses cosh inverse 3. So super easy to do in Desmos. Get our approximation. And if we want the volume, then the only thing we would have to do is multiply by 6. So if we take that and duplicate it, put some parentheses in there, multiply by 6. That should do it. So that'll be our volume, approximated. Any questions on those? Good? All right, so Tuesday, not for you, Tuesday for most of us, we will spend the day reviewing. So the things that you should task yourself with, look at some of the prior exams, look at some of the answer keys, see if there's anything in those that aren't making sense. Look at this My Math Lab assignment that's in there as the practice exam for chapters 6 and 7. Those are the questions that we'll use kind of to guide us through, unless you have a lot of questions from the other stuff. But we'll do stuff from every single section on Tuesday. And then we'll have an exam next Thursday. Wow. It feels like one of those semesters. Flying along. Week 3 is now done for us. Week 3, 20%. Done. 80% to go. All right, have a wonderful weekend. Do a ton of math. Are those the right units? Do a boatload of math. Do a lot of Pascals of math. Anyone that has questions, stay. I will be here for you.
I have a question, but not about math.
Ooh, that's fine.
Attendance, because I remember you get a course out of the college, so
Yeah.
at the high school, the attendance is always like, we have excused absences and unexcused. And so, like, for excuse, you have to call in, but is there
This is
just...
college.
Okay, I was just making
You're
sure.
fine. You're fine. Even though you blew us off on Tuesday.
I know, it was sick.
Are you feeling better?
Yeah, better than I was.
Yeah. It's there's something going
I
around.
know.
All right. Well, I'm glad you're back. Have a good weekend.
It does seem like you might be something to complain about with circles, but,
What are we looking at with the circle today?
all right, this was
Pause on this thing.